Hey students, I got a question here from chapter 20, number 12, and kind of browsing through. It looks like it's got a little subtlety in here, and I'm kind of surprised I haven't really got this question before. Let me give it a try here. Let's see if I kind of throw it in here into the screen here. But number 12 says we have two thermally insulated vessels. They're connected with a narrow tube. It's got a little valve in it. One vessel, and then they give its volume, says it has oxygen, gives its temperature and its pressure. The other one, it gives its volume. Again, and here's going to be the key to it, because this gets a little tricky. There's a little subtlety here, and it's got oxygen in it, so that's going to be important. It's the same material. Well, I guess it's not absolute, but watch. We've got this temperature, we've got this pressure, and then you open the valve, and so what's going to happen is the gases are going to mix, okay, and then there's going to be a final temperature and a final pressure, and so the pressures will equal out, the temperatures will equal out, and that's the questions. What is this final temperature, and what is this final pressure? So if I was trying to draw maybe a picture of this, I guess, okay, I might have, vessel number one, connect with a little tube that's got a valve that can open and close, and right now I'll leave it closed. And then we've got container number two. And they give us the pressure, the volume, and the temperature in each of these. And that's actually very helpful, because then I can find out how many moles is in each of those. And so using the PV equals to nRT for each container, I can say the number of moles is V times R over T. And so if I apply this to container number one, and likewise apply it to container number three, I could put in some numbers here. And so I need to come over here, and maybe so you guys can see it, I'll try to put it here in the screen. But the pressure of the first one is 1.75. The volume of the first one is 16.8. Now, being careful with my units, those are in liters for volume and atmosphere. So when I divide by R, I'm going to use the 0.0821, not the 8.31 that I really like, but this is in the, what I'll call the more chemistry units. I need to divide by the temperature of 300, and that gives me about a 1.19. So I'm going to put down here 1.19. And if you'll allow me to just kind of put these numbers in without putting this in front of the screen, the pressure in the other container was listed as 2.25. Its volume was listed as 22.4. The R, again using the units of liters and pressure of atmospheres, 0.0821. And its temperature is 450 Kelvin, coming up to be about a 1.36. So if it's relevant, we'll see where this gets us. The total number of molecules in this, let's see, 1 and 1 makes 2, and a 3 makes a 4. I'm going to carry 1. That's a 5. Okay. So there's 2.55 moles in the whole thing. And that will be the total when they all mix together. And this is what they are, at least individually. And then once I open the valve, a couple of things happen. Of course, they're at different temperatures. And so things are going to shift around. And you probably saw me do these on other examples. But the energy lost by one of them is going to equal the energy gained by the other. And so one loses, one gains. And so the total change of energy going on inside of here is 0. Now, that's helpful because this then is m C delta T for the first vessel. And then this is MC delta T for the second vessel. And this is where it can have a little subtlety and get a little confusing. Let's see, this one was 450 Kelvin, and this one was the 300. So clearly this one's going to lose energy and cool down, and this one's going to gain it. But also this one was at a higher pressure, so molecules are going to actually go over here also. But kind of thinking of it this way, that, well, then you're going to warm it up. But kind of, even if they kind of flow over here and the volume changes, this has nothing really to do with the volume. And so whatever the molecules that were at the lower temperature, they gain energy, so their Q is going to be a positive. And this one here, I'll call it number 2, is the one that's going to be negative. It's cooling down. Now, I don't really have the mass, but I do have the number of moles. And I do have the molar mass because it's oxygen. So I could replace this right here, the M, well, maybe I'll do it over here, with the number of moles times the molar mass. So I'm going to replace this with N times the molar mass times the specific heat of the oxygen, and then I will go final temperature minus initial temperature. Now, before I do the other one, I'll just point out that that is for the cold one here. So the number of the moles is the 1.19. The molar mass I can look up, and it's oxygen, should be 32 grams per mole. The specific heat I could also look up. But I see something interesting panning out. So I'm going to leave those alone and just put final temperature and then minus the initial, which we are told is 300. And if I do that same for the hot one, this would be the number of moles of the hot one times the molar mass times the specific heat, and this would be final minus initial. So same logic here, but these are different than those variables. This is the number of moles in the second chamber, which we said was 1.36 from this calculation. And then we would have the molar mass, the specific heat, and the final temperature is what I'd like to know, and then the initial temperature is the 450. And here's where I kind of was looking ahead and realized that there would be an MC in each of these, and so if I factor out and divide, because this side's 0, I really don't need to know what they are. And so this becomes 1.19 final temperature minus 300 here. And this comes 1.36 final temperature minus 450 here equals 0. And that allows me not to worry about looking up the specific heat for oxygen, because there's some questions that are going to come up in the next chapter about that. But the molar mass, I don't even need to look up that, although that's a pretty easy one to look up. Anyways, there's my equation for the final temperature. Oops, guess there's a plus right there. And, of course, it cools down, so this is the negative, and this one is the positive. Doing the distributive property, 1.19 final minus, so let me grab my calculator here. I guess this is 1.19 times 300, so this is 357, and 1.36 final minus, and so 1.36 times 450 gives me 612 equals 0. Maybe I can fit it in here. Adding these together, and I think that's the total, isn't that? Isn't that the 255 final temperature here Take 1, 2, okay, and then a 4, carry 1, 5, yeah. And then these I need to put together, so let me put the 357 together with the 610 or 612 and add that, and that's 969, and just barely squeezing it on this paper. The final temperature then is this 969 divided by 2.55, and we're looking at about 380. Nice. Okay. Now, that's one of the questions. What's the final temperature? The other one is the final pressure, and let me just put up here PV equals to nRT. And we can apply this, again, to either the individual sides or the whole collective body. And since they read distributive, I don't know what the number is individually, although it looks like I can figure that out. But to save myself some work, let me not figure that out. Let me just look at the whole collective two together, because the two together, I know the total volume. It's just the sum of the two, and I know the number of molecules. I already added those together. So I could come over here and say, okay, I'm looking for this. I'm looking for the final pressure, because the volume is the two added together. And so that's the 16.8 and the 22.4. And the total number of moles is, again, the two added together. And again, if I'm going to do volume in liters and pressure in atmosphere, let's do R as 0.0821 liters, atmospheres, moles, Kelvin. And I should put my unit here of a mole. So the mole will cancel off, and then these should be liters, liters. Those will cancel off here. And this final temperature here was the 380 Kelvin there. And so now I can finish this problem by getting the final pressure. So 2.55 there, 0.0821, and times 380. So that's across the top there. And then I'll divide that by the 16.8. Let me double check that was right. Yeah. And the 22.4. Okay. And it looks like I'm looking at a pressure of about a 2.03. And that should be in atmospheres, if I'm not mistaken. All right. Nice. All right. Hope that helped somewhat. Take care.